So this is the machine learning and graph databases for better recommendations. Um, hold on. Yeah, so I'm Chris Woodward. I'm a developer relations engineer at ArangoDB. ArangoDB is actually based out of Cologne, and so that's where I'm staying this week. And we also have a small US headquarters in San Francisco. I'm actually from Florida, so I came prepared for the heat. Not so much for the no air conditioning, but whatever, we'll do. But at ArangoDB, I'm involved in doing like creating trainings, working with the community, doing internal development projects, specifically on the ArangoML side of things. And so that's kind of what I'm talking about today. And if you want to connect with me, feel free to reach out on Twitter, or we have a community Slack channel, and I'm Chris.ArangoDB on there, or you can email me, or of course, LinkedIn. I'm always on there. And so this is kind of what we're going to cover today. I put the QR code there just in case you wanted to follow along, but more so what I hope is that after the talk, you can make use of some of the links that are in the slides and stuff like that. The basic agenda is we'll talk about the project that we did for the recommendation side of things, take a look at kind of really brief, what is a graph database, that sort of thing. And then we'll actually take a look at the recommendations. And that'll be the bulk of the talk, is talking about recommendation engines, what they are, and some techniques that we used for our demo purposes. And there are some notebooks linked here that we likely won't have time to get into here. But again, just hopefully that's something that you can make use of after if you want to dive into each of the different topics that we're talking about. And then we'll wrap up with where we see the kind of connection between graph databases and machine learning, and how we went about that. And that's something that we'll kind of cover throughout. So this is the demo project that we worked on. We called it Arango Flix. And this, the goal of this was to offer recommendations, not with the intent of saying like one is better than the other, just more so with, there's a lot of ways to solve this problem of offering recommendations for users. Movies, of course, being a simple one that is easy and there's tons of data available for. And this demo site, we wanted to try and get pretty close to that, but more so allow you to easily switch between the recommendation methods, as well as things like switching between users, and then your normal sort of faceted search options for genre search and language and rating. The data set we use has built-in user ratings that are just they were already there, and so you can filter by those. And then if you want to learn more, is this section on the bottom for the actual query that we use to generate the recommendation. If it's the on ML side of things, links to more information about that technique, as well as the actual notebook. And all the notebooks as well are available through a GitHub repository. So we'll take a look at a live demo of that after we kind of dive into some things, but I just wanted to start out with the what and why of graph. So ArangoDB being a graph database is gonna, make us sound a little biased, of course, but I think the main thing that's always worth pointing out is that when we're talking about graphs versus especially SQL or relational databases, we don't ever come to that conversation saying we're going to replace all your relational databases. They have a very real place, and we don't think that that's something that we're saying should go away. This is an example of something where we feel like relational databases actually shine, where you're more concerned with single rows of data. Maybe you have large amounts of data that you're just constantly needing these sorts of lookups, where you've got, in this example, a product and different tables for price, category, and description, and you can pull that data and kind of go from there. You could get into the whole argument of the no SQL and putting that all in a single document sort of thing, but that's not for our conversation. We're more interested about on the graph side of things, where you want to actually concern yourself with the relationships that exist amongst your products. So in this scenario, we're talking about co-purchasing behaviors, where the ability to start pulling in this data and performing some of these analytics with a relational database isn't impossible, but it does sometimes quickly become infeasible with the amount of joins and stuff that you have to do the equivalent of traversing a graph. It just it just doesn't make sense at a certain point to continue with the relational side of things for this sort of workload. And with the addition of that being that you can continue to build out the relationships that exist with your data and store that information as a real connection between various, in this example, products. And the way that ArangoDB does that is by having what are called edge collections, so actual fully functional documents that store this relationship information and allow you to traverse the graph. We feel that graphs, of course, are the foundation for a lot of the AI and ML stuff coming. I mean, if you look back to, if you're familiar with neural networks at their super basic level, that's a graph, and we're trying to bridge that connection between what you're doing on the machine learning side and the actual storage and graph database side. And this talk will kind of show hopefully one example of doing that. So a quick overview of a graph database at its simplest form is a collection of nodes and edges. So you're describing your graph in kind of two parts, vertices or nodes, and then the edges that connect them. And these edges can sometimes just be simple, almost like pointers, or they can be, like I was describing, full documents that actually describe the relations that exist within the data. As I already kind of went over the join discussion point there. Another thing that's really important when we're talking about graphs and graph databases is that the thing that makes them so powerful is these sort of analytics queries. And things like built-in graph algorithms for k-pass, k-shortest pass, even things like node centrality or being aware of the neighbors that exist in a graph. This is a really common thing where you really just need the closest neighbors that you have in the graph. And the ability to quickly get that information is where graph databases can shine. There's a bunch of use cases. The fraud detection use case, I think, is a really nice one, especially if you're just talking about for the analytics. And sometimes the bigger part with fraud detection is actually the visualization part, where one I always like to talk about is this circular ring detection is a common thing they look for in fraud detection, where you start with someone creating a transaction, and they, user one gives the transaction to user two, and so on until it gets back to user one. And this produces a visual ring that's connected in a circle. And whenever you perform some of these analytics queries on your graph data, the result is you suddenly start seeing a bunch of these rings popping up, and you go, well, maybe this user is, at least we should red flag that maybe and see what's going on there. And this sort of stuff is really powerful on the graph side of things, as this is actually how the data is already stored. And so you can quickly start pulling out these sorts of insights. Supply chain management, that's kind of like the graphic here on the right is a really basic version of the supply chain management, but the ability to graph the relations from factory to, down to even the machine level of a machine in a factory, the parts it takes, and all the connections that exist. So you can say, okay, if I have to replace a part in this machine, that means, it's connected to these 8 other parts. And, we've had customers that go down to the screw level of, if you need a screw for a part for a machine that you're fixing, all of this becomes quickly, immediately available and mapped and persisted that way. So getting access to that is really easy. And recommendations, we'll talk about here. And Customer 360, again, sort of just building out that product example where now we can see co-purchasing behaviors of users, but then also, expanding further out for, building out that customer profile for their other shopping interests, or on the more financial side of things, where you can build out multiple accounts and connections for the user to enrich the application that they're using, so they have the connections to all the places they want them. Network management, I think, is a really nice one because it's a network. We're talking about IT networks. So your infrastructure, it's already a graph. I mean, it naturally exists as a graph, and just for pure mapping purposes is where we see that as a first step. But then you can go on to network management. So offering ways to do upgrades on your equipments, and checking firmware by doing graph traversals. In large enterprises, this is a really kind of daunting thing where you've got these just thousands of nodes per per area of the business, and you have to make sure to keep them all in line and be able to do things like risk management on them and say, if this goes down, what happens to the workforce if we lose these areas, and having backup plans and stuff is where we've seen that. So just kind of like that's really it. That's all I'm going to cover on the graph basics side, and then we'll kind of like start getting into the recommendation stuff. But the high-level overview of sort of what we did with the demo is we start with the data. We actually looked at a couple different data sets. Movie Lens, I think we still even ended up incorporating into what we're using. TMDB is something that gave us, I think, primarily just the movie poster pictures, but looked at a couple things and had our first challenge there of really deciding on one that had user ratings and all the info that we wanted. And then how do we actually start incorporating that into the database, and how do we make sure that our current ML tools like allow for this back and forth? And that was really where the biggest challenge and hopefully our kind of best outcome was being able to persist the data in the database and then having some sort of connection to normal standard ML libraries and tools, so that if you're someone that's already doing machine learning, you keep doing it the way you're doing it, and then you get to use the database and back and forth. And then we actually put a GraphQL endpoint on top, not for any real particular reason. I think it was just a let's do it, and we want to see about the sort of challenges that exist there. GraphQL graph, it to us feels a bit like a misnomer, like it's not the typical graph when we're talking about GraphQL. You can browse data through an endpoint in a similar fashion, but there are details, and that's not really for this talk. But and so we do have this GraphQL endpoint running on what's called we call it Fox, our microservices framework. That's actually a part of our database. So for us also, it was pretty easy to do because we already have the microservices available. And then we have the front end that we did there as well. And for us, all of this existing in the cloud was a big requirement, and so that was the outcome as well. So what is a recommendation system? Well, it'd be recommendation system or engine or recommender system. Probably heard all of those terms, but at the base level, its aim is to provide predictions to either users or to a business. And the way it's doing this is typically from some pre-existing data. I put this business-driven one there as that's, I think, a pretty interesting topic when you're talking about what makes an accurate recommendation or a good recommendation. Because you can have accurate recommendations, and then you can have ones that are maybe more business-driven. And when trying to figure out ways to influence the recommendation that you're offering, this is what's going to kind of decide the good recommendation part. So for instance, like with the movie example, and I don't know for sure if Netflix does this, but they produce their own movies. And so when they're creating recommendations, something they might do is sort of bubble their specific movies to the top. Well, it's still probably relevant. It might not be as relevant as some others. And again, I don't know for sure that Netflix does that, but definitely that's something that we see. And that like almost starts bordering this line of recommendation or advertisement. And for us, we focused on accuracy, but just something to keep in mind. So the data quality side is really more so about it might inform which method you end up doing for recommendations. Like if you have a lot of data it's very feature rich, and it's something, like your use case is for movie recommendations, where you could potentially make use of large descriptions or summaries of the movies that have a lot of useful data. This is something where a more content-based approach is going to make sense, where if you really are dealing with very, very sparse data, this is something where maybe matrix factorization comes in and collaborative filtering, and we'll take a look at those, so getting ahead of myself there. But and then privacy and explainability, I always like mentioning that, because that's just one of those things that as we're going, trying to figure this stuff out, the tracking of how we're dealing with potentially user data and then the outcomes of those things is not usually the first priority for a lot of us. And I just think this article that we have here is really interesting, as it talks about the memoization of data for model building, and the outcome of that being that sensitive user information was available as a result of this model unexpectedly. And so that's like finding out the hard way, is realizing that like, okay, I get the expected results, but then also I can query it and get really sensitive user information. So definitely feel free to read that if you're interested there. Domain specific, this is again tying into more of the approach you might take. And there's a bunch of different domains that recommendations exist with, and we'll take a look at some of those. And then yeah, this is really the three main ones that you typically come across are a content-based approach for recommendations, and then collaborative filtering, and then there's like a hybrid, which we kind of did the hybrid with our collaborative filtering option, which is just really combining this content-based and like matrix factorization or whatever you're using. And then for us, we did a GNN option, so just like a link prediction. And that's just something I included because that's what we'll show off. Here's a good list of the domains and various companies that use them. And so for products on the Amazon side, simple recommendations of other users bought this, so you might like that. Or offering more personalized recommendations for, this matches your specific buying habits, and being able to predict things that are a bit less broad. And this is a big focus for those types of companies as well. And one that I also kind of find interesting is on the job side. So something that we've all seen over the past couple of years has been this big job shift, more remote job availability, but then that means a sort of like onslaught of either job offers or trying to dig through available jobs, and the ability to input your skills and actually get proper recommendations for potential jobs for you, or on the other side for like recruiters, I think is pretty nice. And this is an area that a good recommendation system comes in. Things like destinations, for me, Maps has been quite helpful in recommending coffee places as I've needed it coming from Florida. But Airbnb, of course, recommending based on where you're going and your intended, like your prior like visits that you've done, and like maybe the pricing bracket that you were interested in or the features that you were interested in. And then on the people side, of course, social networks, recommending new friends, recommending new groups to be in. It's like a Reddit sort of recommending based on your browsing behavior. Maybe you'll be interested in this group. On the research side, this is something that we've seen in things like, even in like drug discovery, where you could say, recommending either next steps or recommending new papers based on the papers that someone is currently researching, and being able to actually recommend like the next thing they should read, either based on citation or based on the actual content of that paper. And there's a couple nice libraries out there that that's our whole goal is recommending these papers. On the search side, I think it's pretty easy to argue that Google is offering recommendations at the end of the day. They're either, you could say that through PageRank, and analyzing the actual content, or just your actual, what are you more likely to click on, and tailoring those specific results to you. I don't know if you've had that experience of being able to Google something on somebody else's device or something and realizing that they are actually getting pretty different results, but that's maybe what they're more likely to interact with. And then, of course, for us, Netflix is the big one. If you haven't heard, Netflix had a $1 million challenge for offering better recommendations. The person that won it was using sort of a matrix factorization SVD. If you look it up, it's called like Func SVD, and there's a link also talks about some of the challenges there. But one interesting thing is this Napoleon Dynamite problem that they had while going through it, which Napoleon Dynamite was a pretty popular movie, but they couldn't recommend it. It was just this weird anomaly of, it was just a weird movie at the time, and people either absolutely loved it or they absolutely hated it, and their preferences didn't align on why that would happen. And this was something that cropped up, and I thought it was an interesting one if you wanted to read more about it. That's a pretty good link covering the beginning, noticing the problem, and the eventual outcome. So this is just looking at kind of, when we're talking about recommendations, the existence within the larger enterprise. So we're talking about a pretty straightforward example, but this can get a little complicated. This is from an article that we wrote for like Who's Who in Data Science, but this is also just a nice view, I think, of the steps it can take before that data does finally get to the ML model or whatever actual like recommender logic you have. We'll be focusing on this, just the customer interaction with our front end, and then the sort of back end and storage considerations, and finally what we're actually doing for those recommendations. Okay, and so my timer didn't go, so I want to make sure I'm not going too over here, but I just wanted to show off at least a working demo. This is running on our ArangoDB cloud platform, so feel free to check it out there. But the notebooks and data sets and everything are available outside of the cloud platform as well, just through a repository, and all the links are here. But so yeah, this is the site. You can switch between the recommendation methods at the top. We started out with using just a content base. We have a built-in search engine called Arango Search that supports TFIDF and BM25. But we tried to offer it in a similar way to allow you to narrow down results and stuff based on what you're interested in. And then we even offer a sort of trying to explain why a certain result was recommended. So this user is Arthur, and we're looking at movies he's watched and then movies that are similar to that. And the end result was that it's recommending the Bill Hicks story based on various distances that it has to other movies. And we get different results depending on the method that we're choosing, and some can help explain a bit better. Like I think this collaborative filtering one is pretty good, where we can see, for example, the movie that I think we're looking at Arthur here watched, and then the other users that watched it, and you can start getting a better idea of like why this movie might have been actually recommended based on their co-watching behaviors. And we'll take a better look at this later on, but just something kind of nice to play around with to try and get a better idea on why a certain movie might have been recommended. Where if we get to something like the graph neural network approach, where like 100% of this is done outside of the database, this is a really simple traversal. This is nothing. I mean, all it ends up saying is this is the recommendation for this user. So there's not really much to explain on the database side. There's a lot to explain inside the notebook, which we have available there. But in the database, this is sort of like a benefit we see of using machine learning as well as the database, is that while this is a simple graph, you could begin tying this into the other user profiles and really building this out while also still having really, really fast recommendations, because none of this computation has to be done on the fly. And that's one approach that we took. This is like on the database side, the graph neural network is probably the simplest, but of course, maybe the most complex on the machine learning side. So it's just a little bit of a balance there. Okay. And I guess, okay, maybe this might be actually an okay spot. If any immediate questions so far, otherwise I'll keep trucking along. All good? Okay, so for that site, the general stack that we use for the recommendations, as I mentioned, we have the Arango search for the TFIDF side and the content-based search. And then we just use raw AQL to take a look at user ratings and then getting similar movies. And then for the TFIDF, which is the approach we use for the ML content-based, we just used sklearn. And on the matrix factorization and collaborative filtering side of things, we use the surprise library and the SVD algorithm there. And then on the GNN, we use PyTorch Geometric and Espert for those. And on backend ArangoDB Cloud, we have a Python driver. We actually have two Python drivers. Python Arango is the main one we're using right now. This is something that we've developed with the community as well. And we have another one called PyArango. And the Fox microservices, this is just our microservices framework that lives on the database. And this allows us to install a GraphQL endpoint, which is what we did. And then on the front end, Vue.js, Cytoscape is for that graph visualization. Pretty basic, so open to feedback on that. I know it's probably not the most advanced, but it's pretty nice to use. And then Prime View for the theming. Okay, so the first one we'll take a look at is just this content-based filtering. Okay, so on the content-based filtering side, the benefits of this is that it can end up being very personalized. So rather than trying to make predictions based on, not to oversimplify, but like based on some of the missing data that you have, or some of the existing patterns that we'll take a look at, like in collaborative filtering and matrix factorization, you can really come away with a pretty confident level saying, this movie is actually relevant to this other movie based on actual like contextual information. So the descriptions for the movies that are actually describing them, and you can incorporate additional features like genres or even like taglines and stuff like that. That if you've got available features, you can really build this up, and then you can combine this with other things like watching behaviors and stuff. But the drawback can be that it does require a little bit more domain knowledge than typically other approaches might, where you have to be aware of what features are considered valuable features, and being able to have someone that says, okay, this movie actually is similar to that movie, which we could all probably do that. But for other domains, that becomes a bit more difficult. And it can be fast, and I say it can be because, of course, there's always some restriction with that, especially if you are using a lot of features and you're trying to do this ad hoc. So you're trying to compute similarity scores for a bunch of movies for each individual recommendation. That can just prove challenging. And so this is why a lot of times you're going to end up seeing the final one we look at is this hybrid approach, where you do some of the upfront load and then you do some computation on the way. And then just as a brief definition, I found this from actually Google has a really nice ML course, as well as one that's specifically targeted at recommendation systems. So something we're checking out, and I linked to it there. Content-based filtering uses item features to recommend other items similar to what the user likes based on their previous actions or explicit feedback. I felt like that was just a nice, concise way of saying everything I just said. And so the method that we used is kind of the standard, like getting started with recommendation method. This is TFIDF. It stands for term frequency, so how often a term shows up in a document. Inverse document frequency, how often it shows up across all documents. And then the goal of this is to identify valuable terms based on some input phrase that you might have or something. And valuable meaning like is actually relevant to the document, not something that are typically referred to as like stop words, like a, and, of, the. Those things are going to show up a lot, but they don't actually add a lot of value. And so trying to find these terms that are actually valuable and then ranking them and then getting scores based back on that. There are some problems with this approach, but in general, it's like a good enough approach, and then you can build on it from there. And the one way that you typically are kind of going to progress from TF-IDF is using what's called BM25, and this is really just like an alteration of TF-IDF, which takes into account some other things, such as like the length of the document. Let's say you have a large like corpus, like a large like description or something for like a product, where maybe you do see valuable terms showing up a lot, but if they show up too much, they could potentially start to get like D-ranked essentially. And this is something we want to avoid if the only like crime is that they're in a document that references them a lot. There are some challenges there, but in general, the goal of this is just trying to pick out words that are showing up and considered relevant, and that's one way. I think we'll take a better look at something like the matrix factorization side, and then I think that'll help tie in some stuff there. And we might come back to the notebook just because I don't want to run out of time, but we do have 2 notebooks available, and this is for our Arango search one. This is like really straightforward because it's just all an AQL query. But on the ML side, this does cover a bit more of how we go about using this. And when we're using I'll go ahead and open it. I think we've got time. It's not a link. And all of these notebooks as well, you can just you can run freely. They actually generate a temporary ArangoDB instance, and that instance only lasts a couple of hours, but then it allows you to play around with it, sign in to the UI and everything. You don't have to sign up for anything. It's just it provides you some temporary credentials and everything. But the basic gist of what most of these will do is go through, maybe do some like text, like some data transformations just to like get it ready for the database. But in general, in here, the main thing that we go through and do is use the TFIDF vectorizer method. I was trying to pull that out. There's a lot of like upfront stuff. But once we have those scores, the score that we get is a relevance or like similarity score. And this is the actual output that we're using whenever we bring it into the database. And yeah, the main thing I wanted to point out there was what it looks like once we're actually storing it in the graph. And I think we'll just have to come back to that if we have time. But so once we are done with that experiment, and we actually do this same thing for all of them, we tried to get as unified of an approach as we could, so for the TF-IDF side of things, we're getting a similarity score, and this is what lives on the edge connecting the nodes. And this can be, for TF-IDF, going to be more like movies to movies. So how similar is movie A to movie B? And then when we're doing our graph traversal, we can evaluate these. And taking this approach of storing this information on the edge is what allows you to take advantage of some of the like weighted graph traversals and various techniques that show up in graph databases. But yeah, as I mentioned as well, the like sort of next step, and typically what we find even as the sort of like almost de facto, once you're familiar with TF-IDF, is starting with BM25, as it does solve some of the other challenges that come along with it. And the next method that shows up often with recommender systems is collaborative filtering. This can also offer personalized recommendations, but it is typically a little less personalized because it doesn't require as much domain knowledge, and it sort of is figuring out these predictions like for you, rather than us, specifically saying we want similar movies based on the similarity of their description. This is going to look at existing patterns in the data. And so normally the reason you're using like a collaborative filtering or specifically a matrix factorization approach is that you have very sparse data. So that would mean that you have a large data set and you have a lot of movies and you're trying to do predictions. And actually I'll show you, this matrix is kind of one example where you start out with something like this and you're trying to fill in the gaps. This is like one phase of it. The next phase is actually using a separate matrix with what are called latent factors, where you have so let's take this example for, we have a user over here, user 3, who has watched GoldenEye and Star Trek, and so has user 4, and like an obvious guess here would be that user 4 probably isn't going to like Babe, the movie, as user 3 rated it poorly. But what about for user 3 and 4 liking this Love Actually movie? You can start to make some pretty good guesses based on the other available data here. But one thing that you can go one step further is to say, okay, well, we know that they're just raw ratings here, but a lot of times you won't even have this many ratings. If the best example is like after you're done watching a Netflix movie, what are the chances you actually rate that movie or show? It's pretty low. And what we have seen is like there can be data like this that has a sparsity of 90% sometimes, where it's just like you have not a whole lot to work with. But that little bit that you do have, such as some of these movies, might have other things like genres or release years and things like that maybe you could try and use from what you already have to make these predictions. And this is where you actually end up forming a second matrix like this that has pre-generated like random values. And then as you make predictions, you start adjusting those random values to align with what the actual data was that you have. So if a factor is for genre and you give it a random value and you make a prediction that doesn't match up with like Star Trek for sci-fi, you can slowly begin to adjust these things and get them more in line. And this is this like SVD and this Funk SVD, that one that won the Netflix side of things. This is the approach that they took, where understanding that there's really sparse data, even more so sparse than this, but the goal still centers around the data that you do have and trying to have it align with the existing user data. So trying to figure out if user 3 and 4 are actually going to have similar preferences. And the way that you get there is this would be considered a low dimensional matrix, as there's just the two, the user and item matrix, and that's all we'll cover there. But we use a surprise library with the SVD method in the notebook if you did want to dive in a bit more there. And the final method that we used for this demo was with graph neural networks. We actually have a whole couple-hour-long talk on using this. This is a colleague of mine. He's an ML research engineer on the ArangoML team. And I put a link to the talk that he gives on that. But the overall gist of it is that we are trying to do this graph representation learning, which is taking your normal input graph that you have and transferring it over to more of an embedding space. And there's a couple ways that you go about doing this, and the approach that we took is through the neighborhood encoding. So while you have a network like we have on the left here with U and V, you want to be able to bring it over to the embedding space while it's still aware of the nodes that it was nearby. But the objective here is to get it into this embedding space, and then it'll actually end up being next to other nodes that are similar but perhaps weren't directly connected. And I'll show you, I think, yeah. So something like this, where we've got a network of whatever we're concerned with, and once we do some of this message passing, which is just encoding relevant data about nearby neighbors and bringing it into this embedding space, we can actually start to see clustering behavior that wasn't obvious or didn't exist in the graph as we had it. And you would want to do this for a couple different tasks. For us, the main thing was trying to figure out if it's nearby and it's similar based on the features we're using, then we could maybe form a link. And that link has a score based on how close it is in that new embedding graph. This is also something that comes up on just normal machine learning activities, where if you want to be able to do something like with the CNN here, where in order to be able to do this sort of activity, there needs to be a set number of neighbors. So as it begins to go through, for example, this is just saying we're analyzing this cat picture and we're going left to right, top down. In order for it to be able to do that, there has to be a fixed number of nodes, which is not something that you can normally count on in just your production graph that you're using for your application. So there needs to be some way to shape this graph to still be able to work with your classic machine learning activities. And this is where something like these PyTorch tools and various new external libraries are coming in. And as I mentioned, this was sort of our goal here was on the link prediction side. And so we would that's why that graph that I showed you before was so kind of like straightforward, is at the end of this, we're just generating new edges that say, we think this user will like this movie. And for more info there, definitely check out the notebook. This is kind of our most involved one, and even more so if you are interested on the graph neural network side. We have a lot more information available, multiple webinars and workshops that we've done on that as well. And there is that. And okay, so just to sort of round this all out on our approach of why we feel like this made recommendations better with using graph databases and machine learning. It really comes down to being able to do what you're already normally doing with your application, or if you're more on the machine learning side, already doing what what you're doing with your machine learning, and being able to easily go back and forth and actually store those outcomes, because there's a lot of effort and infrastructure, a lot of time involved in productionizing machine learning models, and getting that data into pre-existing applications can be pretty challenging. And this is where we're kind of building out our ML ecosystem. Right now, we've been developing adapters, we call them, for NetworkX. We have DGL, QGraph. Recently, we released an RDF adapter, not really super relevant there, but if you're into RDF, it allows you to bring your RDF graphs into ArangoDB. We also have this ArangoML pipeline, which is specifically targeted at, if you're doing machine learning, there should be some sort of common metadata layer that exists across the entire machine learning pipeline. Where if you look at certain libraries, there are more coming out that are concerned with capturing metadata. And I mean, this can be anything from just keeping track of the data set you're using to doing things like even storing notebooks or keeping track of the parameters or the features that you had. This sort of ties into needing to have like this feature store. But everywhere that the data goes or any sort of activity, the importance of having this common metadata layer is really the biggest one for auditing. Where if someone comes to you, we came up with this as our CTO worked with a health company, and they were audited, and they said, we need to know where this user data has existed, which activities have ever touched it. And that wasn't really something that they could answer at the time. And this is becoming more and more of a thing where you really have to be accountable for how you're using your data, regardless of who's doing what with it, even if it's not customer facing. And then we also really recently released a PyTorch geometric adapter to the point where our current notebook doesn't actually use it. We just released it like a week or two ago, the finalized version of this PyTorch geometric adapter, and we're still kind of coming up with some updates for it. And then this is sort of the really basic roadmap that we have for where to take machine learning with graph databases. We actually partnered with NVIDIA working with their Triton inference server. This is a server that allows you to serve multiple machine learning models from a single server. And the sort of potential connection we would see here would be the Triton inference server connecting to a model repository to bring in those ML models, but then updating those inferences back to the database and having this sort of loop of being able to continue iterating on your machine learning models while also continuing to keep the data up to date inside of your database. And then the ability, the reason you'd want to do that, of course, it requires query support within the database to be able to actually do something with embeddings, or we're talking about having this sort of data frame support, but we've got to have something that you can actually do with that stuff before it makes sense to bring it in. One thing that we added was a cosine similarity function for inside of the database to make use of some vectors that you might be working with. But in general, you can queries such as we saw with the movie demo, like any similarity outcomes or distance metrics that you might be storing, and actually make use of those along your graph traversal. And this would mean that if you were already doing recommendations, such as what we showed, 2 methods of doing it with just AQL, if you just simply add in the outcomes of your machine learning, the outcome of that is either just substantially faster because there's less computation on the fly, or they're just better because you can take more information into account. And the sort of takeaways, these are just some links to some pretty interesting books and courses that you can read or follow up on. I hope that I have delivered on what I said I would do here, is kind of quickly discuss graph databases, recommendation systems, and then how we see machine learning and graph databases helping out with recommendations. And yeah, if you want to keep learning, definitely feel free. Those are all links to the various places. And these are all the links to the notebooks. If you want to check out those adapters that I mentioned or any of these notebooks, you can also check out the ArangoML repository. And even the ML metadata capture utility is actually also open sourced on there. We also have a summit coming up if you want to check out our ArangoDB summit, and we'll have a bunch of other talks and stuff happening there. But yeah, that was it. Any questions? Any questions or anything?
Is this a managed solution that lives in the cloud, or you can deploy it on your own?
We do have this ArangoDB Oasis. That's our managed solution, but ArangoDB itself is open source. You can freely use the database. We have a community and enterprise version, which is paid version, but community version is completely open source. It's Apache 2 license.
One very strange question. How do you get the data into Arango?
Yeah. So.
Let's say as long as you just retrieve some text from descriptions from movies, well, absolutely straightforward. But if you have more complex application situations, it's becoming challenging. You can allow someone to tap this all stuff in.
And make sure that I understand. So you're talking about how do you get data into ArangoDB, sort of if it's something else like coming from a different utility or a different.
Yeah, coming from a utility or whatever place.
Mm.
Not just that you just pick up the internet because of some user behavior.
So if hopefully let me know if I answer this correctly. But so for instance, one approach that we're taking was with like the adapters, where if you're working with libraries and it's in weird shapes, especially like something that we saw with what was it? I guess DGL is a good example because it's like not, or I should maybe even say more so like PyTorch is a good example because the data that you're working with there is usually I don't want to say simple, but like it's very simple as far as the representations are just usually numbers. And the way that you would represent that in ArangoDB is usually like it doesn't make sense because it's a labeled property graph. So you'd expect to have labels and data, but we do have a way of supplying all of these adapters sort of use what's called our meta graph, where you can easily translate from whatever graph you're working with on that side of things and bringing it in. But this is like kind of you already have your data and then you're using this existing adapter. On the import side of like if it's just a little unknown and you're working with whatever you're working with and you want to bring it in, there's tons of language drivers, or we have an import utility that just imports CSV or JSON as well. So is that kind of what you were getting at?
I think for the moment, yes.
Okay.
Is that meant as a transactional database to provide recommendations on the fly, or more as an analytical database
Yeah, I think it definitely shines on the analytical side for sure. That's, I think that's really a good use case for graph databases as a whole is on analytics. As far as transactional stuff, yes, definitely we use that. ArangoDB is actually a multi-model database. We're graph first, but we're actually can be just used as a regular document store or a key value store. And so that's like a nice benefit. If you're not interested in graph, you can do those for your normal like application uses. And we are ACID compliant in certain scenarios, and some considerations have to be taken. But yeah, as far as like actual transactions go, yeah, we do that as well.
maybe one more question.
Yeah.
It's more regarding the label property graph versus RDF. Do you see RDF still being popular data format in the graph databases?
Yeah, it's interesting. I feel like RDF I actually am pretty interested in. We do see it. We see it like where it's being used. It's like the only thing being used, and we see it a lot in like government facilities. They're using RDF because they've always used it, and they don't really show signs of not using it. But they have people there that are like, we want to use ArangoDB or we want to use proper property graphs, and there needs to be a way to go back and forth. And that's one of the approaches that we took was having this Arango RDF adapter that allows you to import any serialization. It uses the RDF lib Python package if you're familiar, and basically just sort of doing the same thing of how do you bring in, and that's a whole different talk on bringing RDF into property graphs, because there's a bunch of different little weird one-offs. But yeah, I would say I've had a surprising number of questions about it over the last like 6 months even, where I don't hear much about it, but then I would say, yeah, it's still there.